Our first speaker after the lunch break is Alexey Bocharnikov. Alexey has been at the forefront of technology innovation for over 15 years. He brings a unique mix of quantum tech knowledge and cybersecurity strategy expertise to his work at Accenture. Currently, he's an Asia Pacific regional leader for quantum security and director of cybersecurity strategy. Presenting a talk titled Secrets No More, Quantum State of the Art and Advances in Codebreaking, please invite Alexey to the stage.
Hey everyone, let me open my notes quickly. So, quantum. In this talk, I see as my primary objective to talk you through this topic so you can make better decisions. There are so many misconceptions. You all heard this term, you read about it, you watched YouTube videos, and through all the discussions I've been involved into, I rarely see a person that has blocks aligned in the right way. Usually there are so many things that are not right, and that's what I want to help you here. I hope after this presentation, you know what to ask, what to look for, where not to get trapped. So let's go straight into that. The first one, I should say, probably my presentation is built like on those most common questions I see, and they are in the order as they come. The first one, there are two really different things. One is quantum computing, and another one is quantum risk. So when you hear quantum computing, what people refer to is they refer to a problem that they want to solve, and they want to solve it with a quantum computer, which is a physical device. And what they hope to do, they hope to do it much better than you can do classically. Whereas when you refer to quantum risk, you don't need a quantum computer at all. Like the whole thing is very classical. Like the solution to this problem is classical. All the things you're going to do to remediate it are classical. You don't need a quantum computer at any shape or form in any of the steps where you remediate quantum risk. It's all about cryptography. It just happens that quantum computing launched the discussion, and probably because of that, quantum get attached to this word risk, but it has nothing to do with quantum. So I just want to underscore it once again. Quantum computing, a device itself, an algorithm, and the belief to do it much, much faster, the risk is very classical. Now, going to the next one, that's I like a lot. So look, these are 9 terms. People like word quantum. They attach it to all the words when they name things, and that does not automatically put that term into the same bucket. I just put 9 of them, and you're free to think about any other things, and you'll ask me in a moment. So before I go and explain, let me ask the audience. So guys, how many of you, just raise your hand, think that all 9 of them are related to quantum computing? So a quantum computer is implied there to do something. All 9 of them. Anyone hand? The next question, 7. Yeah, take your time, read it. I'm not rushing. No one. I see the whole audience. I'm saying no one because those who are in the front rows don't see those that are in the back rows. 5, half of them. 1, 2, 3, roughly 5. Awesome, 5. Then 3. Okay, roughly half of the audience. 1. Another 3. And no one, like none of the tiles are related to quantum computing. Okay, so the right answer is just 1. Let's go one by one through each of them. So quantum magazine is just like a paper. People decided quantum is a fancy word and named that a magazine. Also, I like very much when in presentations, when people want to name articles, they bring the word quantum and attach it. And sometimes they even use quantum leap, implying that they'll jump so fast and so forward, so no one will see how fast they move. So you should keep in mind, quantum, the word itself, means like very, very small, minuscule. So whenever you hear quantum leap or quantum jump, what they say is that they'll jump so small that you won't even notice how far they jumped. Then quantum internet. That's a complicated one. So whenever you hear quantum internet, what people imply, they refer usually to a thing where they aim to build a network that allows to distribute entanglement between quantum computers, so you do kind of distributed computation. It's not our classical internet that becomes better. It's not like any other thing. It is just a distributed computation on a quantum computer. Though this term is not yet well defined, sometimes people refer to quantum key distribution, and we'll speak about it later. But in most cases, like whenever we speak with academics, what is implied is that you have one computer in Melbourne, another one in Sydney, and you somehow wire them so you have one device. Then quantum terminal, that's a physical place here in Sydney, next to the central station, where government invested, and they built 4-story building, 3-story thing, where they brought all the startups with quantum, and they just called it quantum terminal. Obviously nothing to have with quantum computing. Then quantum sensing. So whenever you hear that one, what you should think about, that's like you have a box, a chest, maybe of a different size, smaller or bigger, and something happens inside. You don't care what happens inside. As an outcome, you receive a classical bit of strings like a reading of some parameter, magnetic field, gravitational force, whatever you want to read, and you just process it on your laptop or on a server. So you don't need a quantum computer, neither inside, nor after, nor before to do that stuff. It's like an advanced measurement device. Quantum-inspired optimization. So that's I like one of the most things among all this one, because that's the cheekiest one. So what people imply here is that someone was aiming to build a quantum algorithm. That's hard. So he started, researched the field, thought thoroughly how can he apply things that quantum can do to his problem, and then came up with a classical algorithm, which is not quantum. But because he thought a lot, he was inspired by quantum physics, by things, how they work. He literally called this quantum inspired, and in this case, optimization. So there are many other things a part of optimization. So quantum inspired, no quantum computing inside. It's just someone learned the field and become inspired and did something classically. And quantum leap we discussed. Quantum computing, obviously, you need a quantum computer to do something better. You hope it will be better, not necessarily always, but you hope that. Quantum risk, that's the one that we're going to speak here about. Cybersecurity problem, cryptography, no quantum computing needed to solve it. And the last one, quantum cryptography. So quantum cryptography, this is a common thing that people in cybersecurity tend to kind of throw. And what they imply is that there's some cryptography that exists, and you need the quantum computer to run that cryptography algorithms on a quantum computer. And that's the only way how you can get protected from quantum risk. So that's not true. Quantum cryptography as a term just almost does not exist. It is some sort of an academic research that's in its infancy, where people try to build advanced cryptography algorithms that are not anywhere close to production, where they try to use quantum computers to do some advanced cryptographic manipulations. But in today's world, in our day-to-day jobs, whatever and whenever you think about cybersecurity and hear term quantum cryptography, it is not in any shape or form related to quantum computing. Now, with that knowledge, I'm sure now you crawl much better through things where people try to kind of trick you and bring quantum computing where there's none. Like if anyone wants to ask any other term you have in your mind right now, let's just try and see if I can help you. If no, we can just wait until the end and bring it at the end. No, fine. Next one. Now, we're going into quantum risk, and the rest of the presentation will be just about the quantum risk. And I wanted to start by bringing to you the recent change, like not that recent, but on the scale of world, like a recent change. And that is about force that drives adoption of the solutions, the remediation of the quantum risk. So before that, it was the security risk itself. The cryptography is vulnerable, my data is not well protected, thus I need to go and fix it. And whenever you go, you need to speak with your executive, with your CISO, with anyone, and try to convince them this is a real problem, this is a real threat, I need to fix it. That was hard. Like you needed people to believe you, to understand technically what's going on, and that didn't work very well. So that was understood by many governments, and what they came up with some sort of help with the ultimate prioritization technique that they use, which is regulations. So today, whenever you go and speak about quantum risk, you probably will use another approach, which is there are regulations there, like whether you like it or not, whether you agree with my statement that quantum risk is a real thing or not, like doesn't matter. There are standards and regulations, and now you need to go and make things work. Now, also there's the third force that I think a lot of people underestimate, but it's super powerful. Now, whenever your organization works, it has a lot of communication with counterparties across the globe, from US, whatever other parts of the globe. Now they have their own data security, data privacy officers, cybersecurity functions. And whenever they adopt the tool set that makes things quantum safe, they will demand that from their partners, because from that point, they won't accept that their data that they consider something they need to protect is protected by means that they consider insecure. So soon, and it happens today, but the more we go into the future, the higher will be the force, the stronger will be the force. Partners will demand from everyone that, guys, you need to go and build things quantum safe, because that's, we think, what's the only way to make data secure. I just want to spend one slide speaking about regulations. I recently found an awesome resource. It was just the day before yesterday, which the link is at the bottom, that outlines all the regulations that government across the world issued. Like there are so many lines. So there are regulations and guidelines. So there's only one country in the world that made regulations a mandatory thing that you must follow, and that is US. And there is just 2 here, but in fact, they have many more. And in US, there is an obligation for companies from different sectors to start doing some steps that make them quantum safe. Like all other countries, and in my example, those are Australia, South Korea, Singapore, and Europe in general, those are just guidelines. So they either in their strategy or in whatever other document that they make public, someone who is a trusted party in that dialogue acknowledges that this is a risk. We must all think about it. There are ways how you can remediate it, but it's not yet a regulation. Now, there is another side, which is the right side, where we have cryptography regulatory bodies. You know, there are bodies in the world that everyone tends to listen to, and what they do, the only thing, not the only thing, like one of the most important things they do, they define what cryptography algorithms and with what configurations you're allowed to use and what is considered safe today. So their job is to look after the different attacks, after the growth of compute power development in the academics about ways how you can break cryptographic algorithms, different cryptoanalytic methods, absorb that and come up with a guideline that tells you, like today, that's the key length you want to use, and that's the algorithm that you are allowed to use. Now, this is the 4 most common one, and recently in US, NIST issued their guideline. It probably was 1 month ago, and in that guideline, they depreciated the usage of asymmetric cryptography algorithms. We'll speak a moment about them, starting from 2030. And going forward, they allowed to use only the post-quantum cryptography algorithms. Now, what it means practically, it means that whenever you have next audit coming to you, they'll come up and they'll take those guidelines, not regulations, they'll take those guidelines and assess you against those guidelines. And if you're not compliant, if you're using something outdated, you'll have an audit point, whatever compliance requirement process you would need to follow in your environment to remediate it. That's all about regulations. All the rest is about the risk itself, like the security risk itself. So I wanted to start from a little bit distant and speak about what's the difference in how you protect data. That's my interpretation. It's not written in a book, or I'm not aware about the statements in a book. So you have matter, like sometimes some things that you want to protect, like physical elements, like a gold or a paper or a letter. And recently we added information to that, like digital information. Like ultimately, when you think about physical representation of something, the only way how you can protect it is by physically securing it. You add guards, you put it in a safe underground, and the way how you can break in is through physical penetration. So if I have more power, if I have like stronger people, I can eventually come up to you and get that data. It may work with the information too, right? You can put it unencrypted on the server into the safe, and you have the same. But it wasn't the best thing you can do, and thus we have these other points here. Another way how you can do things is you can do something with the information and do not disclose what you've done with that, and hope that unless people found the way how you manipulated with your information, it remains secure. So this level of security is based on the absence of knowledge how things work. So you can do it in a matter world, in a physical world, but you can do it with an information, and it's okay. So a lot of people fail back to this mode where the top one doesn't work. They assume that while I keep obscured, like the processes I use to secure my information, I'm safe. So it is kind of a good to have thing, but that's not the position where you want to be. You want to be on the right-hand side. And that's where you use math, like, or other scientific tools to provide security. There, no matter how strong you are. Even more, there's like a famous cryptography principles written by Bocharnikov, where he explicitly states that the internal mechanics of a cryptography algorithm must be known, and security must not rely on the knowledge about how cryptography algorithm works. So you want to be there. All the security levels, all the standards, every time you refer to cryptography, that's this right-hand side. Now, what happens today with the quantum computing evolution, and what I unfortunately hear more and more, is that people, in their response, in their initial intent and impulse to make things quantum safe, they're telling, okay, fine, I won't be using algorithms that are considered secure, but I have other things. Like, no one can get into my environment because I have, defense in depth in general. Like, there are so many other things. Accounts are properly controlled. Like, I have firewalls properly set up. That's fine. Like, you're right, it helps. But you need to clearly keep in mind that you move from this right-hand side to this kind of middle point, where you imply an absence of knowledge to your environment. Next one. I found it very fascinating. So this is the explanation why things are secure. This is very interesting to understand. It will make, it made my life easier once you get it. And that is computational hardness assumption. So have you ever thought that the algorithms we use today, do they provide like absolute security? There is no way anyone can break them, or do they provide reasonable security, meaning sometime in the future, maybe someone can break it? So there are these two big realms in cryptography, and one is called information secure, or in my initial sentence, it was absolute secure, and this reasonably secure. Now, you can build an algorithm that provides like this absolute security, but that is so unpractical. Like, they exist, but they're so unpractical. No one ever uses them. So this information security, it implies that no matter what resources do you use, like this, you have a computer size of a universe, like no matter how big is it, you have all the resources in the world. You cannot break the message. There's just no way you can do it. And that exists, but not practical. All the algorithms we use today, you pick any one of them. They are built on assumptions, and the main of them is the computational hardness assumption. And what it effectively means is that when they were designed, someone came up with an assumption, like sort of a ceiling that defines how much of computational resources an attacker, a would-be attacker, could have when he attacks an algorithm. So those are strong assumptions, but don't take me wrong, those are great assumptions. It worked with us. Those algorithms that we've built 40, 30 years ago, they're still today, they're still secure. Those were the right assumptions. So unfortunately, when those algorithms were developed, what wasn't taken into account, that at some point, the new way of compute will appear. In that case, today we know it's quantum computing that will break those assumptions. And that's what happened today. In essence, you can say this assumption-based flaw was baked into every algorithms when they were designed. And it's still the case when we build post-quantum secure algorithms. We still build them on assumptions. And there's no guarantee that someday in the future, someone will come up with another computational paradigm, whatever it will be, or with novel crypto-analytical methods, with the novel algorithms how to break things, and those assumptions won't hold. If you're lucky enough to be on the first row and to observe what happens when assumption fails. That didn't happen before. In the past, we had algorithms that were depreciated, but it never was at the scale that we see today. where like the whole class of cryptography algorithms fails because underlying assumptions were essentially the same and they are no longer valid. So keep in mind, computational hardness assumption, very fancy thing, just tells you that initially assumed things will be secure given that amount of resources, but those were just assumptions and they tend to fail. Now, in cryptography, there are so many different primitives, like a lot of them. That's not a comprehensive list. That's just to give you an intuition what happens. There are different ways you can do cryptography. Usually, when you take any one system that you use in your production environment, you never use any one of them independently. Usually, you combine them, build them, 3, 4, at least 2 of them, to do anything useful. So for example, the most basic example, whenever you want to send a data from point A to point B, and you want to make it secure, you want to do 2 things. So first one, you want to agree on a key. You want to have a way how over the open channel, when you imply that anyone can listen to the channel, you can exchange some information between 2 parties, and at the end have 2 strings, one on the side A, another one on the side B, and be sure that only those participants in the communication know that secret. This is a symmetric primitive called public key ciphers. So you use it once at the beginning of the session. You establish the key, and then when you start encrypting, when you start sending the messages, you're not using that. Then you go into the symmetric key primitives and you use one of those block ciphers or stream ciphers, and that's where you continuously apply that key and encrypt data. So this key is used while the session is active, and then you need to establish it again. So you always have a combination of those things. Quantum computer didn't break all of them. Like there are so many, and they're all secure. What has happened is that asymmetric primitives, which are here at the bottom, they happened to rely on mathematical problems. A conic example is the factorization problem, where you're easy to multiply, hard to reverse factor. And everyone believed that this factorization problem will stay hard for a much longer time. But it just happened that one of the first algorithms that was developed for quantum computers allowed to solve that problem. And also what happens that you can effectively bring other mathematical foundations that are used for other public key ciphers to the same problem. And thus the whole class of asymmetric primitives was relying on the same mathematical construct where quantum computing happened to be effective, and thus it's no longer considered secure. Sometimes you may hear that symmetric key primitives are not secure anymore. So this is the wrong assumption. It's a little bit shady, but in general, whenever you speak with cryptographers or with academics, they tend to say, and all those cryptography agencies from the previous slide, in their official publications, they never say that cryptography symmetric key primitives are vulnerable. The reason being is that in general, symmetric key primitives are not built on mathematical problems. You do not multiply things there. You do not do any complex math. The only thing you do there, you just substitute and shuffle things. And you substitute and shuffle them in such a complicated way that you assume that if someone intercepts that and they don't know how to reverse that, they will never figure out how to do it, and thus the message is secure. There, the problem, the assumption is that this substitution permutation method is secure on its own. Now, quantum computing, that's another famous algorithm, which is a quantum search by Groover. It, from the first glance, may seem like gives you advantage in conducting attacks through unstructured search, meaning just you can brute force things and you use quantum computer. It allows you to find symmetric key faster, and thus it is vulnerable. But that's not the case, because the consensus is that once you build that search algorithm, the complexity of that algorithm becomes so big, so it's exponentially complex, in fact, and that it outweighs the advantage it gives. So then you have 0 advantage. So symmetric key primitives are okay. AES algorithms, the iconic example, is fine. We still use it. Asymmetric primitives, all of them are done. So they need to be replaced. And there are a lot of other things that we use, and they're still secure. Now, I want to stop for a moment and speak, like, why is it a problem? Why can't I just go and replace? I have these old algorithms, and now I have these new algorithms that need standardized, that are called post-quantum cryptography algorithms. They're built on assumptions that include quantum computer, That means that the problems they have chosen are complex even for quantum computers, and we believe they're secure. Like, what's the problem? What's the issue? The issue is, in one sentence, is that they're not compatible with what you use today. So this table represents digital signatures, not the algorithms that we used to establish key. Remember, there were two blocks here. One was digital signature, another one was key agreement protocols. So this is just digital signatures. And why I want to speak about digital signatures, because it happens they have more problems than another block. And the primary reason for that is, as you see, there are two kind of columns. One relates to size, another one shows relative time. None of the finalists that become now standards have even close numbers to what we have today. So if you take SLHDSA, the kind of third row in the second part, its public key size is 17 kilobytes. This is insane, because for RSA, it's just 256 bytes. So it's 50 times more. Like, none of the systems that we use today, and think about IoT devices where we have a lot of restrictions on computational resources. And in general, like network devices, none of them was developed to handle that a big key. Then you can say, okay, I'll trade the length of the key and will kind of use more power to do computations. There's some trade-off possible. That's like the second line. You see there, you reduce the key to 7 kilobytes, but now your relative time in signing is just 3,000 times more than it was before. That's again insane. That's so complicated. And this is the primary reason why we speak so much now about quantum risk, is because those algorithms that were introduced as post-quantum safe, they are just not compatible with technology, hardware, and software that we use today, and will cause so many issues. Taking past experience, it took forever to remediate algorithms. Like, the basic example from my experience is that one day we wanted to change hashing for passwords that we used in a database, and we wanted to use another hash function that was better, like more secure. And the problem, the obvious problem we faced, is that you cannot do it on your own. You need a user to log in, and then you tell him, like, please change, and then he changes. So for 3 years, you have the old password using old hash, because users are just not coming to you every day. They're not changing that. So with that in mind, migration to new cryptography algorithms will be painful. Now on this slide, I wanted to bring like one data point. There are many data points you can find. I wanted to bring one data point that defines the timeline. Whenever you go and speak internally, you eventually will come up to a discussion about how much time do you have, and the iconic question is when someone will break cryptography. Like, no one can say, no one has a crystal ball, but what you can do, you can bring different facts that allow you to kind of judge, make a better decision about where things are going to happen. Now, people, when they discuss that, tend to focus on the right side. So here is just number of qubits and quantum computers of different modalities thrown on one graph. So that's not the right way to compare quantum computers with each other. They're built using different principles. They are very different. There's, in the industry, no one metric that you can use to equally compare them. But for the sake of this slide, just the number of qubits is OK. You see, their capacity is growing. They're becoming bigger and bigger and bigger. And that's usually when the discussion ends. But there's a second part, which is the left side. That's the algorithms that exist to actually break cryptography. Shor developed his initial idea, 25 years ago now, if not more. And then there were so many improvements to that. Like 2009, there was an algorithm that required 1 billion physical qubits to execute an attack. And the note again, measuring algorithm requirements just in qubits is wrong. There are so many other things you need to keep in mind. But for the sake of explanation to show the trends, we're using just number of qubits. There was 1 billion qubits to actually execute an attack. That was a lot. We had 1 qubit, and there was 1 billion qubits. Like, I have a lot of time to wait. Now, 2019, there was another algorithm that required now 20 million qubits to execute an attack. This is 2 orders of magnitude drop. That's still a lot. I have 20 million qubits, and at the time I have whatever, 10, 20 qubit device. Still, gap is huge. Now, 2022, from the top of my head, there's another class of algorithms appear that are called heuristic. Those are the previous algorithms were proven algorithms, which means they will work every time you launch them. Heuristic on the opposite, they work sometimes. Like usually it means that in practical situations, when I do route optimization, when I use Google Maps, there's no graph that complex that will break my algorithm and it just works, but I can construct a situation when this algorithm fails. That's what heuristic means. So Zapata came with an idea where they converted the problem of breaking a cryptographic algorithm into optimization problem. And thus it became heuristic. And in their approach, they required just 6,000 qubits. Then 2023 January, Chinese scientists come up with an algorithm that requires 400 qubits, which is less than we had at that point in time. It didn't scale, it didn't work. They applied the same idea of translating the problem into optimization problem. They just used another technique. It just didn't work, didn't scale. Now, 1 month ago, there were 2 other papers from Chinese scientists, and just outlining them in a few sentences, they did the same. They found another way how to wrap problem and translate it into optimization problem. And again, they claim they can do it with less than the capacity that we have today with quantum computers that we can use right now. But it didn't work again once you apply it and try to use them on algorithms with the sizes of keys that we use in production. It just didn't work. So the bottom line here is the development in the algorithms area is an active space of research. It's not that we have Shor, that was 25 years ago, and that's it. No, there are so many progress made in that space, and it's much closer than it may think from the distance to the capacity of quantum computers that we have today. Now, if you ever read or heard about quantum risk, probably you heard about this equation. That's the Moscow equation. I can skip it, but I'll be very quick. The idea is that that's the second factor you can use, like how to understand where do I need to start? Should I be quick or am I late? The idea is that you compare your best estimate of when a quantum computer will be able to break a cryptography algorithm with 2 other factors, which is how long do I need to protect my data and how long it takes to change my environment, how long it takes to retool your environment. So once you do that, when you have the gap, which is small, not necessarily negative or positive, but small, that means that your estimates they're obviously estimates, they're close to each other, and that's where you need to worry. Obviously, if you have a huge negative gap, then that's a huge problem. If you have huge positive gap, then you have some time to actually think about it and work on that. So that requires some estimates, and I found that a lot of companies are moving in the direction that they want to have a position. So whenever board comes or a regulator comes in the future and asks, like, there were news, you heard about it, why didn't you do anything? Companies tend to make a safe move to protect them and come up with some statements saying, guys, in 2024, in November, we did our homework. We understood there is an emergent risk or a current risk. And based on our estimates, we consulted with A, B, and C and came up that we're fine, or we're in a risk zone, and thus we started the remediation program. Now, of course, everyone heard about Harvest Now Decrypt Later attack. And at some point, I realized that I assumed that this is a known fact what it is, but there were people in the audience that didn't know. And from that moment, I decided to add 1 quick slide to explain what happens. So data keeps value over time. Whenever you created a data, probably it will be valuable to you for more than a year, but sometimes it spans to like decades. Think about your medical data or some other data about HR records that needs to be kept for years, not decades. Now, it may mean nothing, but an attackers found a way how to use it against you. And that's not a novel thing. It's not connected to quantum computers. That was with us for ages. And the idea is that you intercept data, you sit on it, you don't do anything. You intercept it in an encrypted form, and then you wait for something to happen. Like maybe someone will come up with a much bigger supercomputer. Maybe someone will find a flaw in the implementation of that algorithm. Maybe someone will find a way how to break like the foundational concepts that form security of the algorithm. You just sit and wait. And that was 30 years ago, that is now. The only thing that you remember, this computational hardness assumption, this baked in flaw was always in all the algorithms. Now, what changed with the development of quantum computers is that the tool that will allow you to break messages encrypted today just became known. And now any government, like anyone, tells you that, and even associate this attack with quantum computers because they know I can intercept it. And there's a good chance before data loses value, before time lapses, someone will come up with an algorithm and a quantum computer big enough that I can use, so I decrypt it. I think it's important to outline that there are two interesting assumptions that people make when they think about threats, and they always map them to this harvest now, decrypt later attack, but they don't hold. So first assumption is that whenever attack happens, whenever someone attacks your environment, you live under impression that you can do something. Like I can hire a company, I can shut off the server, I can do something to stop it. No, that doesn't work with this harvest now, decrypt later thing. If someone intercepted your data today, you've lost control today, you cannot re-encrypt it. You can't do anything. If you're unlucky and in the future someone decrypts your data and starts whatever, trading it on the black market to do something against your will, you can do anything. You just sit in the front row and observe. And the second one is, usually people build complicated detection capabilities. They try to get signs of things happening in their environment, and from that understand, is there an attack happening, like what's going on? So this type of attack is a passive sniffing attack. Like it's the hardest one to detect. You will never know it happened, especially if it happened somewhere where you don't have control over the environment. Okay, now we're coming almost to the end of the slides that I wanted to speak with you about. So here, I wanted to try and outline like a canvas for you. What does it mean to become quantum safe? I'm not aiming to explain in all the details, all the bullet points, but what I wanted to do with you is to show you how big is it. There are so many things to care about. So you start from quantum safe components. We discussed post-quantum cryptography algorithms. Now, there is another one, quantum key distribution, that I didn't speak about. So this is the technique where you take like a huge box, a hardware piece. You put it inside A, you put it inside B, and then you connect them using the fiber optics. They most likely will be using the existing one. And the only thing those devices do in this point-to-point communication, they establish a key and a string of bits that is known only to these devices. And then you can consume those keys to actually encrypt data between those sites. So never ever quantum key distribution is #1 solution to your quantum safe problems. Like never ever. There are special use cases for this technology. It has other flaws, other problems that you need to carefully weigh before you go into the implementation of quantum key distribution setup. So I just wanted to warn, and that's such a misconception. And probably again, because quantum, the word itself, is used in the name of this technology, you have quantum risk, you have quantum key distribution, one match another, and I solve the problem. No, you're not. That's a niche technology with very specific applications. And also there are economy-based methods. So there are other things you can do. You remember on that one of the slides with 2 lines, you can drop from the point where you want to be to have this cryptography-based security to one point below where it's built on the methods that someone don't know, or economy-based methods. The iconic example here would be if you think about a database and you apply a key to encrypt a database. If someone steals your database, it will just need to find one key to get access to all the records there, to 1 million records in my example. But if you encrypt every row with a separate key, you effectively increase the cost of attack, and it may be just economically unviable to make this attack. You can come up with other ideas, how to economically protect your data, make it less interesting for an attacker to go after your environment. Now, once you have that, if you have it on your table, it's like nothing. It doesn't make things quantum safe. Just the fact of existence of a QKD device doesn't make things quantum safe. You need to actually put it in action. You need to incorporate it into your environment. And there are many things where it should happen. I tend to ask the audience one question, and I've never heard anyone answer, like, can anyone name any one tool or service or middleware or anything that is modern, not 20 years old, that is modern, where you don't use cryptography. So there is none. You pick anything, and inside you'll have cryptography used for at least something. Usually you start, whenever you think about your environment, from cryptography services, which are internal PKI and HSM systems. This is the tools that deliver cryptography services to other internal consumers. And that's like the most critical asset. You want to remediate them first. Those are obviously non-compliant today with the implementation of new PQC, with the announcement of new PQC algorithms, and with a huge question mark, will your existing tools support that migration? Then you go to network. Like you pick any network protocol on the OC layer, just anyone, there will be cryptography there. Most likely here, you'll be waiting for vendors to come, for standardization agencies to make changes to how network protocols communicate. There's nothing you can do, but you can use some wrappers, like tools that allow you to wrap your traffic into the PQC traffic and thus make it safe. So this is a mix of work with the vendors and decisions for most critical use cases, whether you want to use third-party solutions. Then you go to, this is like the most general term you can think of, IT environment elements, like everything you have. There should be a way how you prioritize things, because cryptography is omnipresent. You cannot go and remediate everything. You start one by one and come up with some metrics how you can do that. Usually here we come to the discussion of the discovery process. I want to know what cryptography they use where, what data is protected with what cryptography algorithms, and having that set, I will make informed decisions about what they want to remediate. And then it may be surprising, but cyber solutions require work too. So take identity management. Like this whole thing, identity management, is just cryptography wrapped with a workflow. Nothing more, nothing less. You have cryptography sitting there to authenticate users, to prove their identity. Like for every step, there is a cryptography. Your identity systems would need to become PQC compliant, which require a lot of efforts. And then now you see that's a huge, huge undertaking. You come to here it's called strategy plane, governance plane. Like how do I do it? And that's one of the most complicated ones from my experience. You need to convince people around you, various stakeholders, people looking after your infrastructure, CISA, product owners, like eventually CEO, to invest into the remediation. That's a costly endeavor. Recently, I heard a very interesting kind of comparison how people describe how long it takes, and I'll share it with you. It takes 3 CISOs or 2 CEOs to actually solve this problem. It spans through so many years that average term of an executive person is less than the time this problem takes to solve. So this is a 4 CISO problem, whatever your actual average time, or 2 CEO problem. Okay, now because of the time, it is 45 minutes now. I have other things to speak about, but do you want to have questions now? We can stop and I'll take any questions from the audience. And then if we have any more time, I can speak about other topics.